Hello and welcome to another Hopper language video. This one is a little longer than usual and it's got a little bit more internals in the language video than I'd like, but it's sort of needed. I'll try not to sidetrack and digress too much and try and keep it short. This video is about the Hopper file system and how it works, how it's implemented, what motivated it the way it is. So recently, let's get started with this example. I finished implementing files and directories for the microcontrollers. So this, I've just compiled this program and I'll load it into the debugger. So it successfully uploaded this test.hex to my Raspberry Pi Pico. This black screen area here is the serial console, serial connection to my Raspberry Pi Pico. So if I F5 and run this, I get it's walked the directory tree of the flash on my Raspberry Pi Pico. So it recursively walked, this walks recursively, exploring the directory tree and the files on this Raspberry Pi Pico. And I implemented this using the Hopper file APIs. So what it is it's the flash of your current running program is put into the flash. So this auto.hexe here, 419 bytes, is actually this current program we're looking at. It compiled it and uploaded it into the hex. So this program is looking at itself. And if I exit out of here and I code gen that program again, what was it called? CodeGen test. Oops, CodeGen. You can see it's 419 bytes long. So when we ran it, auto.hexe was 419 bytes long. So that's it. All right, so I implemented this using the Hopper file API. So I thought it's appropriate time to talk about it because you can use it on your microcontrollers and you can use it when learning Hopper and writing code on Windows. So by way of example, I have another file here called hexdump. What does hexdump do? If you hexdump, say it's hexdump can hexdump itself. So there's the binary in the binary folder, and hexdump is just going to output it to the screen in hex. So how does it work? The main part of the program is this loop down here. It opens the file, end up with a file object, and then it loops through it, reading it. If what it read was valid, process and print it out, go back to the beginning again. As soon as what you read wasn't valid, break out. And this little loop idea with valid is the essence of how the file system works. So it was inspired by .NET to do it this way. There's a number of things we're trying to achieve. One of them is we're trying to come up with a system that works with the garbage collected heap. So it becomes tricky to run a garbage collector when things inside your garbage collector are actually system resources that you're not really garbage collecting, you're actually just keeping a reference to. So the easier way to do that is to never really keep them. So we don't actually keep a file handle in Hopper. The way Hopper works is when you open a file, it reads the entire file into a buffer. And this file thing here is not a handle so much as a buffer. And every time you read, it's reading the next character from the buffer. And is valid is a single way to tell that whether you've had an error in accessing your file system or not. So when you try and read the whole file into the buffer, is valid will tell you, the path was wrong, the file never got opened, you ran out of memory, you couldn't. So any kind of failure of trying to read the entire file into the buffer is reflected in isValid. And then it has a second purpose here, so that when you run out of content, when you read beyond the end of the buffer, isValid turns to false. So here you've got a system of errors where the error is not an overloaded return value, like C APIs like fopen will return null if it couldn't open the file. So the error value is not an overloaded return value, and there's never an exception thrown. So Hopper file APIs the actual API call can never fail. All that happens is that the object it returns is no longer valid. It'll always return an object. There's also no concept of closing the file, because you don't have to close it. It's really just a buffer, which is garbage collected by the heap manager. All right. Where did I get all these ideas from? This was inspired by the .NET file class. And one of the things they did in .NET is this idea, this read all text idea. Same kind of idea, but they read it into a text buffer, whereas mine's just called file. And they didn't do this in the first release of .NET. The first release of .NET was all about streams. So in the second release, they added these APIs, so we can read the whole file in one shot. So it only came out in .NET 2.0, and it's probably because they got so much heat for their stream APIs that people, like novice programmers didn't get, that they probably added these helper functions, and they do exactly the same thing. They read the entire file into a buffer. And part of the reason for this is because the whole stream, everything's a stream kind of paradigm for files dates back to Unix. And at a time where your machine resources were pretty low. So if you're writing a preprocessor that passed its content onto the compiler, you couldn't keep the entire content of that in memory. You had to pass the output from one process to the input of another process, and that's why streams made sense. But in this day and age, our machines' resources are so enormous compared to any file that you and I might work on, that from a programming simplicity point of view and from an error point of view, it's so much simpler just to read the entire thing into memory, which is what we're doing. So back to our examples. So let's go have a look at, let's summarize. Let's go have a look at the file unit. So here it is. These are the file methods. The first four on the list simply work with a path. They don't create an object. They just work with a path. Does a file exist? Delete it. What's its size? What's the time of the last? And I don't do modified time, created time, last write time, all that stuff, or last accessed time. The only time we're ever really interested in is the last modified time. So, which can if the file hasn't been modified yet, it's the created time. So that's the time I get. And that's useful for, Hopper uses all these APIs. So the compiler will use this API to say, has the source code been modified since my last build? So can you run this without building right now? And in my case, you can. Do I need to build? No, because the source code is older than the binary file that was created by the compiler. There's the isValid method, which works on a file object. And as I mentioned, a file object is actually a buffer object. So if you think of it as a buffer, it's easier to understand it. And then I've grouped the key file APIs into two groups. And they're essentially writing and reading. So to open a file for reading, you open it. It exists already, you open it. And you get your buffer, and then you can either read lines or you can read bytes. You can also seek to a position, which the compiler uses a lot. And that position, you can tell the maximum is going to be, you get it from the size API. What's the furthest I can seek? And if you try to seek beyond the end of the file, or because it's so long, if you seek negative, you'll get a result 0. But if you then check is valid after that on the file, you'll get a false. So it'll never fail. It'll just switch is valid to false. Create, how does it work? Create will delete the file if it exists. So it actually doesn't create at all. It deletes. And it'll start you a new buffer. And so at the point at which you're creating, there is no file. And then you can append. So this means you can never append to an existing file, because as soon as you say create, it blows it away. And open only opens for reading. So when you say create, you get a buffer. You append to your buffer. You can either append bytes or you can append strings. It doesn't insert a line break. You have to add that yourself to your string. And then the real create is this flush API, which takes the buffer and flushes it to the original path that you created. One of the simplifications in Hopper that makes a whole lot of this so much easier is the fact that Hopper is by design single-threaded. There's never going to be a multi-threaded version of Hopper. So that means that no one else went and created a file with the same name behind my back while I was in this process of filling my buffer. So between my call to create and my call to flush, no one else did anything. And by no one else, I mean I couldn't either. So I guess I could. I could open another create and do it, but it won't matter, because when I flush, it's going to overwrite it. It's going to overwrite the current one with another one. Anyway, that's how the file APIs work. And a lot of Hopper is written in Hopper, and you can go and look at the source and see how it works. So let's do a bit of that. So let's move on to something a little more complicated. Let's go and look at, so if we look at edit.options in the editor, you get this file with curly braces and commas in it. And if you're familiar with JavaScript, you'll recognize this as Java code, or what people are calling JSON, which is a data format that is actually in JavaScript. So this is the dictionary definition here, and this is a single dictionary, a dictionary with a single item in it called where the key is build options, and the value of it is another dictionary. And inside that dictionary, it's got 5 members, and their keys are also strings, and their values are true and false, so Boolean. And what we're looking at is how the options in the editor are stored. So these options on this menu are stored in a JSON file on disk. So how does this work? And if we go and, what's the easiest way to look at JSON? Probably the editor. Oops, why didn't I see that? Source, editor. There it is. So if I go and look at under commands, if I go and look at options, yeah, it's including, here are the options. So it does have a dictionary in memory. The dictionary, where the keys are strings and the values are strings. So, and this is, I could have made these actual false values rather than strings containing false values, but my JSON files are compatible with JavaScript, so I wanted to keep it so that it would be, round trippable. So when you first load up and register your menus, it initializes them, and then it loads them from disk. So there's a load method here. Creates a path. There's some path APIs, and all the path APIs are all written in Hopper. main function they serve is that you end up with slashes between your components of your paths, but you only end up with one slash rather than two. If it exists, then use the JSON unit to read it into a dictionary. So the result from the, and this again is this APIs that can never fail. So it returns true or false if it succeeded, and the result is a reference argument, which is a dictionary again of variants. So you can have anything in, you can have strings in there or other dictionaries, etc. And that's how it loads it up. And the save option is similar. To create a path, JSON write. And I'm just assuming it always succeeds. I don't bother to check the error result, which is a bit sloppy and lazy, but such is life. So if we go and have a look at the JSON unit, there it is. You have the source code to all of this so that you can use it too. It can export a list, so it can serialize a list. And it can export a dictionary. And it can read them as well. So when you write out a JSON file, it takes a path. If the file exists, it deletes it. It's kind of redundant because inside create it does the same thing, but it makes it for clarity. It tells you what it's doing. And then it just exports the dictionary at the top of the recursive stack that is the JSON structure. And then at the end of it, it flushes it. So what it's doing inside export is it's creating a massive buffer of this JSON file, and then the actual file write happens when it flushes the buffer over here. Yeah. There's a lot of assumptions about the fact that it's going to succeed, but it tends to succeed because the APIs never fail. So this would fail if I ran out of disk space, for example, then the flush would fail. And so if I checked, I should really return. This should really be, I should return is valid like that. Would be a better way of doing this. But I'm not going to do that without testing it. Since this is all used by the toolchain, and it uses the same tokenizer and scanner as the Hopper compiler does. So it uses the same parser and the same tokenizer. Because the tokens are, curly braces and things. Yeah. Lots of reuse. Very nice. So we can go and look at a more complicated JSON file. The toolchain, which is, say, the preprocessor. So when the preprocessor, we can go and look in the debug obj, the temporary output. If we look at our original program, hex dump .json, this is the intermediate output from the first pass of the parser, which is called preprocess. So what it found that our JSON, our hex dump program pulled in all these other units. And then it picks up all the definitions of functions, their arguments, etc. So current directory set is a setter which takes a single argument, which is a hidden argument called value. It's a string. So again, JSON file. And then it passes this on from the preprocessor to the compiler. Okay, let's see, what else can I say about the file APIs? Oh, keep doing that. Paths. So Hopper paths are limited, and you can see this in the path unit. What's a valid path character? So valid path characters are limited to letters or digits and a slash and a dot, and that is it. So you can't put a space in a path ever, which means you can never have ambiguity on the console or in if you're calling another launching another exe, you can never have ambiguity between the file path and arguments, because you're not sure if the space is in the path or if it's between two arguments being passed to the executable you're trying to launch. So no spaces in paths, no underscores in paths. Why? Well, no really good reason, other than we can always add, but it'd be difficult to take away. So I don't allow underscores in the names of identifiers. So I figured they're ugly, I won't allow them in the paths either. But you could easily add them. You could add them to the entire system by changing just one API. I also wanted the file system to work on all platforms in exactly the same way, which is tricky nowadays. So I chose the / rather than the / as the path separator. And my reasoning for choosing it wasn't because I was a fan of one system over the other, like Linux versus Windows, for example. My reason is that the / is already used to escape characters in strings, so like /n for end of line, or /n/r, or for it to escape Unicode characters, etc. So the / is already used, so the / is not. So we might as well use the / for like if to put a quote into a string, you escape it with the /. So the / wasn't used, so I decided to use the / for paths. I also decided to make paths not be case sensitive, because at least one of our platforms does not have case sensitive paths, and that is Windows. The Mac is confused in that state because it tries to be a Unixy platform, but it doesn't have case sensitive paths. And then of course the Unixy platforms have case sensitive paths, and by a derivative of one of those is littlefs, which we've currently got running on the Raspberry Pi Pico, which does also have case sensitive paths. So my workaround to make paths work in a non-case sensitive way on the case sensitive platforms is that all the file APIs always lowercase them. So if you pass an API into one of the file APIs, like create or open, it converts it to lowercase before it does anything with it, which means you can't get a mixed case or uppercase path onto your Raspberry Pi Pico's flash. It'll always be all lowercase. So it solves the problem. It's not necessarily pretty, but I was favoring having no failures and never confusing, never using an incorrect case and wondering why you're not getting your file back, or wondering why you can't find your file. Yeah. Path API is also inspired by the .NET versions of the same things, like combine. So combine takes two parts of a path, glues them together, and it'll put in a missing / if there isn't one, but you won't ever end up with multiple consecutive slashes. And in another interesting, so there's two interesting bits of source you can browse. The one is the path unit, which is under system path, to see how paths work and how extensions work. Another interesting bit of source to browse would be under the shell source folder. There's the directory command. So under directory command, you could browse this source to see how folders work and directories work. The directory unit is very, very similar to the file unit in terms of how it was thought out, and it's based on those .NET APIs, the static APIs, that there's no real directory object. So many of them are one-shot, like does it exist, does the directory exist, I want to delete the directory, etc. And then in a similar way to files, this thing that looks like a directory object is actually a buffer again. But in this case, it doesn't load it all up into memory. Actually, it's not a buffer. It's more like an iterator. So like the for each for each which iterates through strings, or it's an iterator, so it actually is a little wrapper for an actual directory on your file system. So you can create or open just like files, and if you open, you get your directory iterator, which means that you can ask it how many files it's got in it or how many directories it's got in it, and then you can go fetch one of them. So fetch item 0, item 1, etc. up to count -1. So, and you can iterate through them like that. And this returns paths, not directory objects or file objects. It returns paths as you iterate through your directory. The time, last modified, created time, etc. also just takes a string. So largely they're just strings, except for this iterator object that you can open, and so that you can step through the content of a directory, and then you can recursively call it and step through again. So the create doesn't even return anything. So it just takes a path and creates a directory. It doesn't even return anything. So the iterator is only used to read. And again, if you're iterating through, you can also check if you're still valid. So if you called one of these things with something that doesn't exist, it would switch your iterators valid to false. But like I said, if you look at the directory command, you can see how the directory unit works by just studying the source code of the directory command. Yeah, not sure if it still does, but it used to use, I don't think it does anymore. It used to use delegates for callbacks, but it doesn't anymore. Yeah, okay. So we've learned about how the file system works, how I used it to put the current content onto the flash on your microcontroller, and the fact that files are just buffers, and you've learned that there's a directory and a path unit as well. I think that's enough for this video on files, directories. You've learned about JSON and the fact that we have a JSON parser that you can use to read and write JSON files built into, it's part of the source. You can use it in your projects. And I think that is enough. So thank you for watching, and I encourage you to watch more of the language videos.